In this video, we will talk about root finding. In particular, we will apply the self-consistent iteration method or the bisection method to find roots of algebraic equations. The bisection method is used to find roots in a continuous function between two given points, provided that the root is between those 2 points. The method involves repeatedly bisecting of the interval and ultimately reaching the desired root. It's a very simple and robust method, but it's relatively slow. This method is also called the interval halving method, binary search method, or the dichotomy method. Okay, so let's look at the method. Let's suppose that f of x is a continuous function in an interval from a to b. And let's suppose that f of a and f of b have opposite signs. Then, by the intermediate value theorem, we know that there must exist one root, at least one root, that lies between a and b. At each step of the method, we divide the interval into 2 halves. And we do that by defining a midpoint c, which is equal to a plus b over 2. And we evaluate the value of the function at that point, f of c. Now, obviously, if f of c is 0, then we have found the root and we can stop. But usually that won't be the case. So f of c will have a sign, and we look at the sign to decide which side the root is. So if f of c and f of a have opposite signs, then it means the root is between a and c. And so in that case, we set b equal to c, and we repeat the process. So that means we pick the left interval and we discard the interval on the right of c, from b to c. So we just select the next b to be equal to c to do that. On the other hand, if f of b and f of c have opposite signs, then that means the root has to be between b and c, and so we discard the interval between a and b, and so we simply set a equal to c and repeat the process. So we continue this procedure again and again until we get close enough to our result up to specified tolerance. After a number of iterations, the value of f of b and f of a will be very close to each other, so we can say that the root of the polynomial is basically between a and b, but if a is practically equal to b, then we know that that's just the root of the polynomial. And here it is again with a figure. So this bracketing procedure. So let's suppose the root is here. We can evaluate, we pick 2 points, one on the left of the root and one on the right. And the root is somewhere in between. Now, f of a is negative and f of b is positive. And in the first iteration, we're going to evaluate f at the point a plus b divided by 2. And that turns out to be positive. So that means the root has to be between that point and a. Okay, so that's the midpoint between a plus b over 2, between a and b. So if f of a and f of c have opposite signs, then that means the root is between a and c. And so in the next iteration, we set c equal to b, or actually b equal to c. So b becomes this point in the next iteration. So the next iteration will evaluate this situation. So then again, we look at the sign of f of a, f of b, and we look at the midpoint, and then again we decide where the root is, and so we repeat this process until we get close enough to the root. Okay, and here's a C++ implementation of this. So let's suppose we want to find the root of a polynomial x cubed minus x squared plus 2. So we want to find for which x this polynomial vanishes. Okay, so first we define some parameter, error parameter or tolerance. Let's pick 0.01. So we just want to find the root with 2-digit accuracy, let's say. First of all, we define a function that represents the polynomial. So that's the function, and it returns x cubed minus x squared plus 2. So we want to find the root of that function, where that function vanishes. Okay, so here we have created another function that finds the root. Now, this function takes a and b as an argument and follows the procedure we just described. So first it checks if f of a and f of b is negative. If it's not negative, then we get an error message. You have not assumed correct a and b. Basically, you're not bracketing the root. So you need to pick an f of a and an f of b such that the product is negative, so that they have different signs, so that we know we are bracketing the root. Okay. Then we set c equal to a first, just so c has some value. So that just initializes c, basically. But then we're gonna update its value. So then we have a while loop, and the while loop continues while b minus a is greater than this specified tolerance or error parameter, in this case 0.01. So if the difference between b and a is greater than that, then this loop keeps repeating itself. And first we find the middle point, then we evaluate f of c, and if that's 0, then we break the loop. Otherwise, we check if f of c times f of a, so if f of c and f of a have different signs, then that means the root must be between a and c, so we set b equal to c. Otherwise, if f of c times f of b is negative, we set a equal to c. So that means the root is between c and b. And then this bisection function is void because it's not returning anything, or we could make it return something, but instead it just prints c to the screen. Okay, so here let's try some value double a equals 5 and b equals 10, and let's try and find a root by calling this bisection function. We get an error message, you have not assumed correct a and b. That means f of a and f of b have the same sign, so we're not bracketing the root. Okay, so let's try a different value. Let's try an a minus 5 and repeat this. Okay, now we get a root that's minus 0.99. We suspect that the root is minus 1, but remember we have set the accuracy here to only 2-digit accuracy, so you're not going to get exactly minus 1. If we want more digits of accuracy, we can add more zeros here and repeat this process. Of course, it's going to be slower. The more accuracy we want, the slower this method will be. Okay, so now we get minus 1 up to at least several digits. So this is usually displayed to 6-digit accuracy. So if you have more than 6 digits here, this will be displayed as minus 1. Okay, so this demonstrates the bisection method. Now let's talk about the self-consistent iteration method. So let's again suppose that we want to find the root to the algebraic equation f of x, which is x cubed minus x squared plus 2 equals 0. So we want to find the root of this function f of x. We want to find solutions to the equation f of x equals 0. Okay. We can try and rearrange this equation like this. So let's take x cubed to the left side and x squared minus 2 to the other side. Then this would look like this. And then we can take the cubic root of this equation. So we have x and then cubic root of 2 minus x squared. Now here we're looking for a solution where x squared is lower than 2, so that this quantity here is positive. But it could also be negative. What's important is that we're seeking a negative root of x, basically. Now x here shows up on both sides of the equation. So a way to try and solve this equation is to start with some initial value or initial guess for x and then plug it in here, evaluate x using this equality, get the new value, take the new value, plug it in here on the right hand side, and then use that expression to evaluate a new x, and then take the new x, plug it back to the right hand side, and then keep iterating like that. So formally we write that as an iteration equation that looks like a sequence. So each term of the sequence depends on the previous term through this equality. So xn plus 1 is minus this expression where xn is the previous value. And we do that for the first step where n equals 0, and then n equals 1, n equals 2, and so on. That's just numbering the iterations. If we implement that, we'll see that it converges to the root, which is x equals minus 1, after just a few iterations, if you start with an initial guess that's reasonably close to the real root. Now, in general, the self-consistent iteration method is very easy to code. You don't have to do all this bracketing, and it usually converges very fast if the iteration is stable. But it's not guaranteed to be stable. And if the method, if the iteration is unstable, then it diverges very, very fast. Or if the initial guess is poor, again, it will diverge very fast. On the other hand, the bisection method is a little more complicated to code and may converge more slowly, but it's guaranteed to always converge if the solution is bracketed. Okay, so now let's look at an implementation of the self-consistent iteration method. I'm going to modify the program we had before. I still have this bisection method in the program, and I'm just going to add another function, the self-consistent function, and again it's going to be void. It will just return a root to the screen. So it takes some initial guess x as input. We don't need two inputs, we just need one initial guess, and then we initialize some temporary variable here, and we check if the previous value of x and the current value are greater than this tolerance parameter, which is a global parameter here that we defined here. Okay, and then as discussed in the slides, we first set x previous equal to x, and then we evaluate the new x from minus the cubic root of absolute x squared minus 2. So we find the next step in the iteration, and then we compare the two. So we compare x to its previous value. And if the difference is larger than that tolerance, we repeat the iteration. Otherwise, we stop. And then we just print out the current value of x. Okay, and then in our main function, we can define a double, let's call it initial guess for x or init x. And let's give it some value. And then we call this self-consistent method, and we just pass this as an argument. That's the initial guess. So let's run this. Okay, so we run this, and we get the root with the bisection method is -1.0006, and then the root for the self-consistent method is again close to -1. So they're both close to -1 here, up to the specified tolerance, which here we set it to 10 to the -3. So it's going to be accurate to 3 digits, basically. If we want better accuracy, we can set a smaller tolerance here and run it again. So then we get -1 for both cases. And it's worth keeping track of the number of iterations here so that we can compare which method converges faster. And as you can see, the code for the bisection method is larger, whereas the code for the self-consistent method is a lot smaller. The method is a lot easier to implement. But again, remember, the self-consistent method may not always converge. If it converges fast. Otherwise, it will blow up fast. So it's a bit of a double-edged knife. On the other hand, the bisection method will always give you a root if you're bracketing the root. So it's more robust. Even though it's a little more complicated to code and a little slower to converge. That's it for this video. Thank you for watching.